This is section 9.3 in Trig, finding polynomial models. We're going to be looking at some examples here on page 571 in the book. I want you to take a look at this first example. I'll zoom in a little bit more on it. What we have here is a linear function, y equals 5x plus 3. And we've picked some x values, 0, 1, 2, 3, 4, and 5. Plug them in, and these are the values that we came up with. 3, 8, 13, 18, 23, and 28. Now, what I want you to notice is that when you subtract these values, and it does not matter which direction, if you decide you're going to subtract 3 minus 8 and 8 minus 13, it really doesn't matter, as long as you're consistent subtracting the y values. So if you want to think about it as 28 minus 23, and then they put that difference between the two values on the next line. Kind of looks like some kind of reverse process on Pascal's triangle, even though that's really not what's going on. So, taking these two values and subtracting them and writing the value beneath. This is the first set of differences. The first set of differences. I want you to notice they all ended up being the same non-zero number. And how many times did it take me to do that? One set of differences ended up giving me the same non-zero value all the way through. Okay, so let's see what happens on the next example. F of x equals x squared plus x plus 3. So we took some values from -1 all the way up to +5, plugged them in, and we got some different y values. And we subtracted them. 33 minus 23 is 10. 23 minus 15 is 8. And you could tell that as we did this the first time, we did not get the same non-zero constant. But, so that was our first set of differences. Then we tried it again. But this time we're using the differences from the first round. Excuse me. So 10 minus 8. 8 minus 6. 6 minus 4. 4 minus 2. 2 minus 0. And each time we did that, folks, we got a non-zero constant value all the way through. Now, there's nothing magical about the non-constant 0 other than the fact that it is the same number. Now, it took me 2 differences for that to happen. Look at the next one. Y equals 2x to the third plus x minus 10. And we plugged in some values and found some y values. And we started subtracting. And when we did it the first set of differences, they did not give me the same non-zero constant. And when we did it again, we did not get the same non-zero constant. And when we did it again, 60 minus 48, 48 minus 36, 36 minus 24, 24 minus 12. Oh, look, we got the same non-zero constant. But it took me 3 sets of differences before that happened. Now, what's going on in these different examples? Well, match up the number of differences with the degree of the polynomial. It's a third degree polynomial. It took 3 differences. It's a second degree polynomial. It took 2 differences. It's a first degree polynomial. It took 1 difference. That's what this theorem is saying. The polynomial difference theorem. Says the function y equals f of x is a polynomial function of degree n if and only if, that's the if from geometry, for any set of x values that form an arithmetic sequence, the nth difference of the corresponding y values are equal and non-zero. In other words, the degree has to match the number of differences. There you go. Kind of layman's terms on that one. So grab your machine, because we're going to try it. Okay, so we're taking the differences between the y values. So 56 minus 35 is 21. See if I can zoom out just a little bit more. So you can see everything I'm doing. Okay. Obviously, 35 minus 20 is 15. 20 minus 10 is 10. 10 minus 4 is 6. 4 minus 1 is 3. So clearly on the first set of differences, we did not get a non-zero constant. That means, folks, that this is not from a linear polynomial. We're not talking about a line for this thing. So we're going to try it again. So we take the differences. 21 minus 15 is 6. 15, that's 5. That's 4. And that's 3. Clearly, we did not get the same non-zero constant, even on the second try. So when we do it the last time, though, we get the same number all the way through. So it took 3 sets of differences before we got the same value. Therefore, this came from a third-degree polynomial. So when it says, find the polynomial model for these points, we know that we're dealing with a third-degree polynomial. What does a third-degree polynomial look like? Well, let me show you. A third-degree polynomial has a cubic term, and it has a quadratic term, and it has a linear term, and a constant term. Now, you'll notice that I used A, B, C, and D for my coefficients because I'm going to need to find out what those coefficients are. And it may end up that some of those coefficients are zeros, or maybe none of them are zeros. But we need to find out what they are. Now, so how many coefficients are there that I need to find out? Looks like 4. So a third-degree polynomial has 4 coefficients to find. It's always 1 more than the degree because of that constant term at the end. Okay, so how am I going to find this? Well, if I have 4 coefficients to find, I need 4 points. Where do you think I'm going to find 4 points? Yes, from the table. So pick your favorite 4 points. I don't really care what 4 points you use. I'm going to pick these 4 points. If you want to pick something else, you pick something else. But I need 4 points. And I'm going to make 4 equations. Now, just for fun, I'm going to put my equals y on the other end. All right? Hopefully that won't confuse a whole lot of you. But the point 420, so appropriate for National Joint Variation Day. Coming up this Friday, I think. Friday? Yes, Friday is April 20th, right? Celebrating National Joint Variation Day. We celebrate all the directly related variables. Major holiday in Algebra 2, but it really should be a carryover holiday to the trig family as well. All right, so from that coordinate 4, 20, we plug in the 4 for the x and the 20 for the y. That gives me, well, 4 to the third. What's 4 to the third? 64 times a plus, and 4 squared, right? That would be 16 times b, and 4 times c, and lastly d equals 20. And my next coordinate, 3, 10, well, 3 cubed would be 27 a's, and 3 squared would be 9 b's, and 3 times c, well, that's just 3c, and 1d equals 10. And 2, 4, that gives me 2 to the third would be 8 a's plus 4 b's plus 2 c's plus 1d equals 4. And 1 comma 1, well, that's just going to give me A plus B plus C plus D equals 1. How do you think I'm going to solve this thing? That's right, folks, matrices. So let's see here. I got 64, 27, 8, and 1, 16, 9, 4, and 1, 4, 3, 2, 1, 1, 1, 1, 1. So interesting. I see a lot of kids put zeros down this column, and when they put zeros down this column, it ends up giving them an error matrix, and they don't know what to do. Of course, in my equation, I have A, B, C, D as a 1 by 4 matrix, and then a final 1 by 4 matrix on the other side of my matrix equation looks like that. Now, how am I going to solve this? Exactly the way we did it before. We'll call this matrix A. We'll call this matrix B. What am I interested in? I'm interested in A inverse B. We talked about left multiplying. So, I'm going to whip out the handy-dandy calculator here. So, we're going to go to the matrix section. Yes, my calculator looks a little bit different than yours because mine's an old-style calculator. I want a 3 by 3, 64, 16, 4, and, oops, what am I doing? I need a 4 by 4. Somebody stop me. 27, 9, 3, and 1, 8, 4, 2, and 1, and 1, 1, 1, and 1. So that's my matrix A. Then I'm going to go back to the matrix section and edit matrix B, which is a, oops, 1. Wait a second. I think I said that. Yeah, I said that wrong earlier. What was I thinking? I said 1 by 4. I can't believe myself. There's 4 rows in one column. My goodness, I'm losing my touch. That's okay. The medicine will kick in soon. All right, so I've got my matrix B. And so I want A, but this time I don't go to the edit section. I stay where I'm at. I want matrix A. I hit the inverse button, right, which is right above the squared button. And then matrix B. And it tells me that I have those values, and I know I'm pretty good at my math, but I sure could use some fraction help. Not really, I don't really need fraction help, but I'm going to use it anyway. So I could go to my math button, go math, fraction. Can't believe I'm actually showing this to a bunch of students that should know what 1/6, 1/2, and 1/3 look like, but okay. That's funny. It didn't even change 0.5 to 1/2 or 0.3 repeating to 1/3. That's hilarious. Okay, all right. I'm sure you can do that. Right, so when we write our equation, we have all the values that we need. 1/6 x to the third plus 1/2 x squared plus 1/3 x. And I don't have to include the 0 at the end because we automatically know that that's the case. So there is my polynomial model for this particular situation. Okay, next one. I have another set of numbers, and let's see here. We need to take the differences. You know what, maybe I'll just zoom up so you can see the numbers better, because that's awfully hard to see. So we have negative 2,100 142 minus negative 1104. So my first difference is negative 1038. Negative 1104 minus negative 490 is negative 614. Negative 490 minus negative 168, negative 322. Negative 168 minus negative 30 is 14. Oh, I typed the wrong thing. That doesn't seem right. Negative 168 minus negative 30. Oh, that's better. Negative 138 negative 30 minus 8 is negative 38, and 8 minus 6 is 2. Okay, clearly it did not happen in the first set of differences. So I've got negative 1038 minus negative 614, negative 424. Negative 614 minus negative 322 is negative 292. Negative 322 minus negative 138, negative 184. Negative 138 minus negative 38 is negative 100. Negative 38 minus 2, negative 4. Clearly on my second pass I did not get the same values. Okay? Negative 424 minus negative 292. I really hope I'm doing all this right, because I don't want to have to do this over again. Negative 292 minus negative 184, negative 108, negative 184 minus negative 100 is negative 84. Negative 100 minus negative 40 is negative 60. Clearly it did not work out for the third difference. Negative 132 minus negative 108 is negative 24. Negative 108 minus negative 84, negative 24. Woo! This is looking good. Negative 84 minus negative 60 equals negative 24. Yay! It worked. On the fourth set of differences, we got the same non-zero constant, which means this is a fourth degree polynomial. We know what fourth degree polynomials look like, right? Ax to the fourth plus bx to the third plus cx squared plus dx plus e. Just for fun, whoops, I'm going to throw my y on the other side. We're going to take how many points? We need 1, 2, 3, 4, 5 coefficients. Whew, my goodness. 5 points, and we're going to take those 5 points, since that's what I chose, and I'm going to plug them into the polynomial to find out what's going on here. So I can write my equations. 5 to the fourth power, what do we got? 625a plus 125b plus 25c plus 5d plus e equals negative 490. Sorry, I'm running out of room here. Plug in a 4. We got 256a plus 64b plus 16c plus 4d plus e equals negative 168. 81a plus 27b plus 9c plus 3d plus e equals negative 30. 2 to the 4th, that's 16a plus 8b plus 4c plus 2d plus e equals 8. A plus B plus C plus D plus E equals 6. So those are my equations. And yes, I'm going to change that to a matrix system. I'm not going to rewrite that whole thing out just for sake of time, but I will go into my matrices, edit this. It needs to be a 5 by 5, 625, 125, 25, 5, and 1. 256. Oops, that's 256. 64, 16, 4, and 1. 81, 27, 9, 3, 1. 16, 8, 4, 2, 1. 1, 1, 1. So once I've got all that entered in, I'm going to go back to my matrix section and go to Edit, Matrix B. It needs to be a 5 by 1 matrix with negative 490, negative 168, negative 30, positive 8, and positive 6. And then I can go back to my screen. Now, quite honestly, I've done all that other stuff. Sorry. Can't use the second enter feature because I've typed in a lot of other stuff. So, matrix A inverse matrix B. Okay, you'll notice that the the coefficients are listed right out here. We have one for the fourth power, the the squared power, and the linear power. So we have y equals negative x to the fourth plus 5x squared plus 2x. We had a 0 for the constant and a 0 for the cubic term. So I didn't have to include those. Question that you might ask yourself is, can we use cubic regression? If you go into the regression features of your calculator, you'll find cubic regression. Yes, we can, but we're only going to use that to check it because I need to see your matrices and the fact that you're using your matrices. Thank you very much.